Welcome back to Applied Mathematics. In this video, we're going to be rationalizing. No, not trying to make an argument make sense. We're going to be working with the mathematics of rationals and trying to turn expressions into things that follow the rules for rationals. Specifically, there is one rule that has not come up prior to this video. A simplified rational may not include a radical in its denominator. So if I have something like 1 over the square root of 2, this is a rational, it is a fraction, it has a square root, a radical, in its denominator. So this rational is not simplified. It needs to be reduced. Usually when you're trying to reduce a fraction, you look for a common factor that you can divide between numerator and denominator. When it comes to dealing with a radical, you have to do things a little bit differently. The process is called rationalizing, but it's a very straightforward process. We're going to multiply by the square root of 2 in the numerator and the denominator. When we do that, 1 times the square root of 2 is the square root of 2, and then the square root of 2 times the square root of 2 is the square root of 4, but the square root of 4 is just 2. So we haven't changed the fraction, we haven't completely gotten rid of the radical, but the preferred form of a fraction that has a radical in it is you can have radicals in the numerator and not the denominator. That rule of thumb makes doing operations on your fraction a little bit easier, right? Trying to find a common denominator between root 2 over 4 and root 3 over 7 is a lot easier than trying to find a common denominator between 1 over root 2 and 1 over root I don't even remember what I said, root 7. So that's kind of the justification here. And whenever you have a square root that is in isolation, the process is very straightforward. Sometimes we can make things a little bit messy. Right? If we have, let's make this even messier. Let's call it 7 over the square root of 12. Well, before I try to rationalize this, I might try to simplify a little bit, because I know that root 12 is the same thing as 2 times the square root of 3. Right? 12 is 4 times 3, and the square root of 4 is 2. I've used that as an example in a couple of videos because, well, it's an easy number to work with. Once I have done that, I recognize I don't have to multiply by root 12 in the numerator and denominator. The only thing I have to worry about with the root is the 3. So let's multiply by the root 3 in the numerator and denominator. When I do that, I'm going to have 7 root 3 over 2 times the square root of 9. Square root of 9 is 3. And 2 times 3 is 6. Right, so we can rationalize something that has a square root in the denominator. If it has the square root and other stuff in the denominator, then it's still the same process. But that does actually still rely on the other stuff is multiplication and division. If I have addition, everything goes out the window. 1 over 1 plus square root of 2. We know that this is not a simplified fraction because it has a radical in its denominator. So we have to rationalize. If I tried just multiplying top and bottom by the square root of 2, I would end up with 2 over square root of 2 plus 1. I'm sorry, square root of 2 plus 2. Because I have to distribute the multiplication over that addition. So we need something more sophisticated. Before I get into actually finding that more sophisticated tool, I did want to mention, does this come up in the world? Yes, absolutely. In previous video on simplifying radical expressions, we talked about what to do with addition and subtraction and multiplication. I kind of glossed over the fact that I never talked about division. And that's because this is what it looks like when you try to divide a radical. 1 divided by the 1 plus square root of 2. That's what division with a radical looks like, and so that's where we need this technique. And this technique is the conjugate. The conjugate of 1 plus square root of 2 is 1 minus square root of 2. So let's go ahead and multiply top and bottom by 1 minus square root of 2. In the numerator, we're just multiplying by 1, so we get 1 minus square root of 2. In the denominator, we have to multiply this all out, so it'll be 1 minus root 2 plus root 2 minus root 4. The plus root 2 and minus root 2 cancel each other out, and the square root of 4 is 2. Now, let's just put that over here. So I have 1 minus square root of 2 all over negative 1. Dividing subtraction by negative 1 changes the order of the subtraction, so my final result here is the square root of 2 minus 1. Or negative 1 plus the square root of 2 if that makes you happier. There's no right or wrong choice between those two options. One more example where things can get a little bit messier in this. How about something like the square root of 6 over the square root of 5 minus 3. Again, I recognize that I've got a radical in the denominator, and I have, in this case, subtraction, which means that I have to be use the more powerful technique of the conjugate pair. The conjugate of root 5 minus 3 is root 5 plus 3, and I'll multiply that in the numerator and in the denominator. In the numerator, that's going to be root 30 plus 3 root 6. In the denominator, that's going to be 5 minus 9. And 5 minus 9 is negative 4. This is one of those places where you're convinced that there has to be something else you can do, but actually that's it. That's the end of the story. Probably I would simplify this a little bit by bringing the negative in front. But yeah, 30 plus 3 root 6 all over 4, that's the best you can do. I can try to make this a little bit messier by putting addition in the numerator as well as the denominator. Something like root 2 plus root 5 over root 2 minus root 5. This is something that a lot of students get thrown off by because all of a sudden we're doing things a little bit too closely related, right? The conjugate pair to root 2 minus root 5 is root 2 plus root 5. And that's exactly what's currently in the numerator. That is entirely a coincidence and doesn't at all change what we're supposed to be doing. We're going to have to distribute in the numerator. It's going to be a pretty nice expression because we'll have root 2 times root 2, which is root 4. We'll have root 2 times root 5, which is root 10. We'll have root 5 times root 2, which is root 10. And we'll have root 5 times root 5, which is root 25. In the denominator, we'll have root 4 plus root 10 minus root 10 minus root 25. And we can get a little bit of cleanup going on here. So we'll have 2 plus 5 plus 2 root 10. I've changed the order a little bit, right? I took the square root of 4, which is 2, and the square root of 25, which is 5. The ones that actually work out, and I brought them in front to make my life a little bit easier. And then I've got 2 square root of 10, so I can simplify by combining some like terms. In the denominator, I'll have root 4, which is 2, I'll have root 25, which is 5, and then the plus root 10 and minus root 10 will cancel each other out. So my final result here is 7 plus 2 root 10 all over negative 3. Again, if I want to simplify, I'll probably bring that negative in front. It's not technically wrong to have a negative in the denominator of a fraction, but it's generally frowned upon by most mathematicians, so taking that last step and cleaning up a bit is probably a good idea. All right. A bit of a short video here. Probably means I flew through talking a little bit too fast, but I think that's good enough, right? Not a whole lot to talk about on this subject, just paying attention to when you have radicals in the denominator. If it's just multiplication, then you can multiply by that square root to clear it out. If it has addition or subtraction, you're looking for a conjugate pair. I do want to mention that if you have a cube root or a fourth root or something else going on, the techniques that I've talked about in this video aren't quite powerful enough to get there, but those happen so rarely in application that I think it's okay to leave it at this. Right? And with that, that's actually the last video in the course. So thank you for joining me throughout the entire course, and maybe I'll see you in another one.